Okay, so hi everyone. Welcome to the second lecture on quantum algorithms for optimization. The topic of today is about a different kind of optimization algorithm which are based on quantum oracles. So before we start, I put some materials on my website related to the course, so you can check online if you want. There are the slides of the course and also some references that I would recommend if you want to know more about the topics we covered during the course. And I think the slides are also online on the website of the organization. Okay, so just a quick reminder of what we saw yesterday. So yesterday was about optimization inspired by physics. We manipulated Hamiltonians and ground states. And some properties of these algorithms were that there were very general algorithms applying to a broad class of problems. As we saw, ground state computation contain a lot of optimization problems, in particular QAOA optimization and so on and so forth. A second property of most algorithms that we saw yesterday was that the running time was often unknown, but we were expecting that it would be significantly smaller than the best known classical optimization method. Okay, people expect that you could achieve maybe exponential speedup with using the adiabatic theorem and so on and so forth, but this is complicated to prove. Last property was some of the methods we saw yesterday were kind of adapted to near-term architectures and hybrid computers. Okay, like QAOA, variational method, they may be useful even on a noisy quantum computer. So maybe let me start asking, do you have any question about what we saw yesterday? Okay, so let's move to today's topic, and I'm going to compare the properties of what kind of algorithm we're about to see. So first, today's is more oriented towards computer science. Okay, so the algorithms, they are much more combinatorial in nature. We'll talk a lot about complexity theory, running time, and also they are more problem specific. So they are less universal as what we saw yesterday. They are really adapted to specific classes of problems. On the positive side, we will be able to give very precise running time guarantee. Okay, so compared to yesterday where there was some unknown about spectral gap and so on and so forth, today we'll be able to characterize precisely the complexity of the algorithm. They will give us quantum advantage, so quantum speedup. However, as you'll see, this speedup is often moderate, like polynomial speedup, not exponential speedup. So with this respect, this kind of algorithm, they are more adapted to long-term, large-scale, fault-tolerant quantum computers. So this is a kind of algorithm that you may expect to run when you have a good quantum computer with very good quality qubits, etc. So this is really about the long-term picture. So this is a recap of the topic that we'll cover yesterday, that we will cover today on the right. Essentially, there will be three families of techniques that I will explain. There are much more than that, but we'll just focus on three representatives. Starting with the easiest algorithm, which has been discovered a long time ago, and then moving to more recent results. So first we'll cover some results about algorithms that are based on the so-called Grover search technique, and we'll see application to minimum finding and minimum spanning tree. Then we'll see a quantum algorithm for computing the gradient of a function, which is an important object in optimization theory. And finally, depending on time, we'll cover some Monte Carlo algorithms, and in particular for solving linear programs and escaping saddle points. Okay, so quantum oracles. So oracles are going to be the central topic of today. This is an assumption that we will need for all the algorithm we'll study. So what is a quantum oracle? This is a way of specifying a particular kind of input access. Okay, so you have a problem that you want to optimize, and we are making some assumption in terms of how can you collect information about the input. So let me give you the mathematical definition. Let's assume the input corresponds to a function f. Okay, it takes as input integer and it returns integer. It could be much more complicated than that. I mean, the input could be anything, just represented as a mapping from, let's say, integer to object. Now, an oracle is a unitary operator, which is provided to you. And what it does is it evaluates the function on any superposition of input values of your choice. Okay, so you can set up a superposition, such as, so let me use that one maybe. Okay, so you can set up a superposition over input indices. Okay, so choosing the amplitude is up to you. Now, when you apply this magical unitary operator, what it will do is it will update the second register by computing the corresponding outcome of the function f. Okay, so we don't care about how the unitary UF is implemented in practice. This is an assumption of the model. I mean, this is given to you. So the classical equivalent of this model is something called the classical oracle. It does something very similar, which is you can choose an index I and it will give you f of I. So what is the difference between the two models is classically you can only evaluate a single index at a time. On the quantum case, you can evaluate a superposition over multiple indices. So the quantum model is at least as powerful as the classical one because you may decide to put all the amplitude on the same index I, and then you would recover the classical oracle. But you could also be more clever than that, and maybe you could decide to kind of distribute the amplitude over multiple indices, and in that way, maybe you can collect information about the entire input function by doing few quantum queries. Okay, so when we talk about oracles, we often aim at minimizing how many times we will use the unitary UF. Okay, so whenever you want to apply UF on a state of your choice, it will cost you 1 unit of computation, let's say. So this is called a query. It can be classical or quantum, depending on what kind of oracle you are manipulating. And the number of times you use the oracle is called the query complexity. Okay, so why do we focus on the number of queries? Because this is often the bottleneck in the algorithm that we will look at in a minute. Okay, so often it is the case that actually simulating UF in practice is going to be the most expensive operation in the final algorithm. So you really want to minimize how many times you need to apply this unitary transformation. Okay, so this is a very important definition. So if there is something not clear, please ask a question now about this definition of what is a quantum oracle. Okay, so this object is studied a lot in computer science, and in particular in quantum computing, because it helps us give very precise guarantee about the running time of algorithm, lower bound and upper bound. Yes, please.
You said at the beginning that there are some probable quantum advantage. Those quantum advantage take into account the implementation of the oracle?
So the question is about the probable quantum advantage that we are about to see. Do they take into account the implementation of UF, the oracle, right? So it will be a quantum advantage in terms of how many times you are using the quantum oracle compared to how many times you would need to use a classical oracle. So the actual implementation cost of the oracle is doesn't enter the picture, right? This is something else. So we assume that implementing UF is something that cannot be sped up by itself in some sense. Okay, so it's also called a black box input because we don't care about the actual implementation of UF. This is as if it was a black box. We only care about how many times we need to use the black box. So let's start with a few simple examples just to digest this model. So here is an example of a problem that could be phrased as an oracle problem. So your goal is to compute some property about an input graph. Yesterday we talked about max cut, for instance. So you could define the function f representing the input as being the list of all the edges of the graph. So the graph is unknown initially, but if you decide to query indices between 1 and 9, this is a number of edges, then the oracle would tell you what are the vertices belonging to that edge. Okay? So for instance, you may want to know, is the graph connected? What is the size of the maximum cut? And you would like to make as few queries as possible to the description of the graph. So let me give you a very concrete example of what a quantum algorithm may look like when you have quantum oracle. Yes?
There is a question in the chat. I think it refers to the previous example on how much qubits at UF in the origin space, how much qubits in the destination space. I think it has something to do with the f of I.
Yeah, so essentially you would need as many qubits as needed to encode. Like if f of I is taking value between, I don't know, 1 and 1,000, then you would need as many qubits as you need. Of course, you may have oracle for which the image of f is something that requires a lot of bits, then you would need more qubits. I mean, the oracle would manipulate more qubits. Okay, so I would just like to give you an example of a quantum algorithm that is using oracles. This is a very well-known algorithm, which is one of the first discovered quantum algorithms. I guess most of you know what it is. It is called the Bernstein-Vazirani problem, and it solves the following task. So the function f, it's not representing a graph, the edges of a graph, it's doing something else. F is taking as input a binary string of size d, and it outputs 1 bit, and this bit is obtained as a linear function evaluated over z2. Okay? And we don't know what is the linear function. So the coefficient a1 up to ad, this is d bits, and we don't know what are those bits. And your goal is to query an oracle to f, making as few queries as possible in order to compute what is a hidden linear function. Okay, so let's start with classical oracle. So could someone tell me if you have a classical oracle, so you can just evaluate f with classical query, what would be your strategy to compute the function? Does someone have an idea? Yes? Yeah, exactly. So what it suggests is to make a first query, so maybe let me write it down. So first query is going to be with x equal to 1, 0, 0, 0, and f of x will be equal to a1. And then you can proceed with x being 0, 1, 0, 0, 0. You would get A2, etc. So the answer is, classically, with classical oracle, you would need D queries. And it's not too complicated to convince yourself that this is the best you could do. Okay, there is no classical algorithm that can compute the function using fewer than D queries. Now, what if you have this magical unitary that can answer a quantum query as well? Go back. Okay. Don't want to move. Okay, so what we are about to see in a minute is if you have a quantum oracle, then you only need to make 2 quantum queries to compute the hidden vector. So this is a huge quantum speedup in terms of how many queries you are doing. And the algorithm is pretty simple. So here is the quantum circuit solving this problem. So it is acting on 2D qubits. The register on the top, they are going to contain the solution, so the vector A1 up to AD. And the vector on the bottom is going to be used to control the quantum oracle operator. So let's proceed step by step. Initially, you start in the all zero state, then you apply Hadamard transform on the top qubits. So here is the state that you obtain, a uniform superposition over all possible bit string on the top register. Then you apply the quantum oracle on the state. So you would obtain the following quantum state, and then the operation on the bottom register. And what happened is something very nice. The outcome of the function f is going to be mapped to the phase of the superposition. It's not too complicated to see why it is the case. And then you will apply a second quantum query, UF, which is going to erase the contents of the second register. So the second register will be mapped back to a superposition with 0 contained in the last part. Okay, so we arrive at that state. So last operation is again to apply Hadamard transform on the top register. And if you do that, you'll see that the final state is just a basis state which contains the value of the bits A1 up to AD, and then a bunch of 0 in the last register. Okay, so maybe just to detail the last step. So why the Hadamard is giving you what you want? Well, because the final state, so if you look at the final state, sum of -1 f of x, x, so just focusing on the first register, this is also equal to, so there is a normalization. So this is also equal to 1 over square root 2, 0 plus -1 A1 x1 1. Okay. And then you tensor multiple time AD XD 1. Okay, so the state has a very simple structure. It's a tensor product of just single qubit superposition, where the phase is going to be 0 if and only if the product between A1 and X1 is equal to 0 or not. Actually, there is no X1. It's just like that. Okay, and when you apply the Hadamard on such a state, it gives you the value of A1, and then A2, etc., up to AD. Okay, so it was just to give you an example of what is an algorithm that takes advantage of quantum oracles. Okay, so now let's move to optimization. Okay, so how can we use oracles to solve optimization problem? So this first part is about exploiting the properties of the Grover algorithm. So let me ask, who knows what is the Grover algorithm? Okay, so half of you. So this is one of the most famous quantum algorithms and also one of the first discovered quantum algorithm. What it does is it solves a very general task. It is going to search in the domain of an oracle whether there exists an element that satisfies a predicate of your choice. So it's something that is used to search in the domain of F if some property is satisfied somewhere. Here is an example of a predicate that you could use. Let's say you want to know if there is an edge that contains the vertex number 3. Okay, so there are actually two such edges. If you use classical query, then if you are very unlucky, you may have to query all the possible indices before computing the solution of this predicate. So classically, you really need to look at the entire table of the function f in the worst case. Now, Grover algorithm can answer the same question by using quadratically less query compared to the classical setting. So this is often presented as a quadratic speedup for solving a search problem. So actually, Grover is doing something more than that. What it does is it not only tells you whether there is something that satisfies the predicate. Actually, if there exists an element satisfying the predicate, it will give you a uniform superposition over all the solutions to the given predicate. Okay, so in the previous case, there were two solutions, like two edges containing vertex 3. So the outcome of Grover is not only the answer yes, but it is actually a superposition over the two indices corresponding to the two edges incident to vertex 3. And this is going to be important in a minute. Okay, so this is like the actual statement about Grover algorithm. If you are searching in the domain of F, and if there are k solutions out of n possible solutions, then preparing such a superposition would cost you root n by k quantum query to the oracle. Okay, on the other hand, classically, you would need to do n classical query. Okay, so how can it be useful for us? So let me present you a very simple algorithm, which is called quantum minimum finding. So quantum minimum finding is the most general minimization problem that you can imagine. You have an arbitrary function f, and what you want to do is you want to find the smallest element in the table of f. Okay, so we are making no assumption about the structure of f. So this is an optimization problem in which the function can really be anything. So it's not very realistic, but let's see if in this scenario we can already do something. So of course, classically, if there is no structure in f, then finding the minimum would require to query all the possible indices. So classically, the complexity is n. Now, how Grover algorithm can help us find the minimum? It's not immediately clear because the predicate of being a minimum is not really a valid predicate, right? It is something that depends on the entire table of f. So you cannot just execute Grover algorithm. You have to be slightly more clever than that. So here is how you can find the minimum by using Grover algorithm. What you'll do is you will start with a guess, which is just x equal 1, y equal f of 1. Okay, so this is your current guess of what is the minimum in the table. And then you will improve the value by repeating the following steps. You will apply Grover algorithm on the input using the following predicate, which is x prime is a positive solution if it evaluates to something less than y. Okay, and now using Grover, you can prepare a superposition over all such solutions. And by measuring the state, you would obtain something which is smaller than y and sampled uniformly at random. Now you can convince yourself that this kind of, so let's see an example. So you start with this value, and Grover will prepare you a superposition over all the smallest element. Okay, and then when you measure, you will get one of them at random. So let's say this is what you get, and then now you update your Grover algorithm, searching for something which is less than 3. So these are the possible candidates, and let's say you obtain that one, this is the minimum. Okay, so you can convince yourself that this is going to converge very quickly to the minimum, like about log n steps. So it converges very quickly because Grover is actually giving you solutions which are sampled uniformly at random among all the elements smaller than the current guess. Okay, so this uniform sampling provides you a very quick convergence rate. And now the overall complexity is easily shown to be root n again by property of Grover algorithm. Okay, so the conclusion is finding the minimum actually costs you root n quantum queries compared to n classical queries. Okay, so you could solve concrete optimization problem using this approach. Let's say you care about max SAT. This is a very hard optimization problem, which is NP hard. You have a SAT formula, which is given as conjunctive normal form. And your goal is to find an assignment that maximizes the number of satisfied clauses. Okay, so a lot of application for such a problem. Now what you could do is you could compile the formula into a quantum circuit that simulates the oracle. In Qiskit, there are some classes that can do it for you. And then you could just use quantum minimum finding, and it will give you a solution after root 2 to the n quantum queries. Okay, so a very straightforward quantum speedup for a very hard problem, but this has a provable running time. So actually, this kind of application to Grover can be pushed a little bit further in a much more complicated way. So I would suggest, for instance, looking at this kind of contribution in the scientific literature. It has been shown that there are some binary optimization problems related, for instance, to constraint satisfaction, for which you can encode the problem into a Hamiltonian, as we saw yesterday. And then, instead of doing a naive adiabatic evolution, which may be very slow because of very small spectral gap, there are some non-trivial way of combining Grover with adiabatic evolution, such that when the spectral gap becomes very small, Grover will give you a way of jumping across the spectral gap. Okay, so it's kind of a very nice combination between Grover algorithm and adiabatic evolution. And by doing that, you can even achieve a running time which is strictly less than 2 to the n by 2. Okay, so Grover is something that can really give you probable way of achieving this kind of complexity when it comes to binary optimization. Okay, so far so good. We know how to find the minimum by doing root n queries when the input has n possible values. Now, as you may expect, this is not really a good optimization algorithm in general. Like as a standalone optimization algorithm, if you want to find the minimum just by applying this algorithm, it's not going to be very efficient. Because typically the size n of the search space is gigantic, so root n query is already too much. So is it useful at the end? So what we'll see in a minute is it is actually useful, but it has to be used in combination with other techniques. And typically, a first step is going to be reducing the search space of minimum finding to something much smaller than capital N. And then in the smaller search space, we'll achieve a quadratic speedup, which overall will give us a non-trivial quantum algorithm. Okay, so let's have a look at a concrete problem for which quantum minimum finding will give us some interesting running time guarantee. And this example is about graphs, and in particular about something called minimum spanning tree. Maybe before that, if there are any questions about quantum minimum finding, the general algorithm? Okay. So minimum spanning tree. So this is a combinatorial optimization problem which asks you to solve the following optimization task. You have a graph with weights on the edges. And your goal is to find a spanning tree for which the sum of all the weights is as small as possible. So what is a spanning tree? A spanning tree, there are two examples in red. It is something that, it is a subset of edges of the original graph that connects all the vertices together. So for any two vertices, there is a way of moving by just following red edges. And it is a tree because there is no loop in the graph. Okay, so you cannot visit the same vertex twice by using different edges. Okay, so here is an example of a spanning tree for the graph on the left, and another example on the bottom of a second spanning tree. Now, once you have selected the spanning tree, the weight is going to be the sum of the weights of the edges that belong to the tree. And you would like to find the spanning tree of minimal weight. Okay, so it has important application in terms of efficient exploration of network, for instance. So maybe you may think that, okay, let's try to use quantum minimum finding, and let's say we construct an oracle that enumerates all the spanning tree. And then we just apply minimum finding and it will return the smallest spanning tree. Well, if you do that, you would need to do exponentially many operations because there are exponentially many spanning trees in general. So you have to be more clever than that, and you have to really exploit the structure of the problem. Okay, so just what would be the oracle in that case? Like a reasonable oracle would give you, for each edge number, the vertices that belong to the edge and the weight of the edges. Okay, so by doing one query, you collect two information at a time, the two vertices of the edge and the weight of the edge. Okay, this is a reasonable oracle that you may expect to be able to simulate in practice. Now that is the answer to the problem. Classically, it is known that the best complexity is going to be m, where m is the number of edges in the graph. So essentially, you have to query all the edges. Now, quantumly, what we'll see in a minute is a quantum algorithm that requires making root n times m queries, where n is the number of vertices. Okay, and because m is less than n squared, this is a provable quantum speedup. Okay, so it is of a polynomial order, the speedup, but it is a provable one, and it is actually the best possible one for solving this problem. Okay, so let's describe the quantum algorithm, starting with a classical algorithm which will speed up by using quantum minimum finding. So this is called a Borufska algorithm. It's an iterative algorithm that will construct the minimum spanning tree by adding edges to the solution one after the other. And it works as follows. So initially you have the original graph with no edge included in the spanning tree. Now what you'll do is, for each vertex, you will include in the spanning tree the edges of minimum weight. Okay, so this is going to be the first step. So you see, let's look at the top vertices, for instance. There are two incident edges. One is of weight 1, the other is of weight 4, so the smallest one is the left one. So we include it in the spanning tree. And we repeat the same process for all the other vertices. Okay? So after one step, we have a collection of edges It's not a tree yet because it does not connect all the vertices together. This is what is called a forest, so a collection of trees. And now we repeat. And how do we repeat? Well, we look at each connected component in red, and we look at all the outgoing edges from that component. So for instance, the component on the left, there are two outgoing edges. One is of weight 4, and the other one is of weight 5. And for each connected component, we add the edge of minimum weight. And this is what we obtain. So at that point, we arrived at a spanning tree, so we can just stop the algorithm. And there is a mathematical proof that if you do that, you will actually compute a minimum spanning tree. Okay, so if at that point it was still not connected, you would have repeated a few more steps. So that is a classical algorithm. Now you can imagine how we are going to speed up the algorithm using minimum finding. But if we go back in time, the first step was about finding a collection of minimum weight edges, which we can speed up using quantum minimum finding. Okay, so quantum minimum finding will explore all the edges in superposition, and it will tell us what are the smallest weight edges. Okay, second step, now we have to do minimum finding again, but over a smaller set of edges. So this is actually the final statement about the algorithm. So quantum minimum finding will help us accelerate each step by finding the outgoing edges of minimum weight. And actually, we use some improved version of minimum finding in which we want to solve not only one, but k minimum finding problem in parallel. And there is a nice property, which I'm not going to detail in the talk, but when you want to solve k instances in parallel, you can do it in root k times n quantum queries, which is better than a naive k times root n repetition. Okay, so when you want to solve the problem in parallel, there is even a speed up with respect to how many parallel instances you want to solve. Okay, and the mathematical proof for the running time uses the fact that after t steps, the number of connected components has decreased at least exponentially in t. So again, the algorithm requires logarithmically many steps. It converges very quickly to a spanning tree. Okay, so that is the overall complexity. First step is finding n edges, at most n edges, so you can do it in root nm. Then finding at most n by 2 edges, so root nm by 2, etc. So overall, the complexity is root nm. Okay, any question on, yes?
When do you stop the algorithm?
You stop the algorithm when the set of red edges is connecting all the vertices together. So the criteria is you have n minus 1 edges, essentially. So you see at each step, you are increasing the size of the red component, and you stop when it connects all the vertices together, which will appear when there are n minus 1 edges in the connected. So there is some proof that tells you that you will never create loops or cycles into the graph using this kind of algorithm, right? So there is some proof of correctness, which I'm not detailing here. Okay, so that's a pretty simple quantum algorithm that shows you how combinatorial optimization can be accelerated using very basic idea of Grover algorithm together with classical technique. There are much more advanced applications of this kind of technique, which are still being actively studied by researchers in the domain and trying to solve much more advanced combinatorial optimization tasks. So I would just like to give you a few examples of other applications that you may find interesting if you care about this kind of topics. So what we just saw is application of quantum minimum finding. This is a a foundational paper from 2004 that contains other nice applications, for instance, solving single source shortest path. Now, more recently, a much more advanced application of Grover type technique is to accelerate something called graph sparsification, which is a very important object, which consists of starting from an initial graph. You want to remove as many edges as possible, and you want to preserve some spectral property of the graph. So that is something very important. And again, this can be accelerated using some non-trivial application of Grover and other techniques. And it has applications in terms of solving certain type of linear system, like so-called Laplacian system, and also finding approximation to max cut, min cut in graphs. Another nice application is about dynamic programming, which can also be accelerated using Grover types technique with application to the TSP or the minimum set cover problem. Okay, last series of application is in relation to backtracking and branch and bound techniques, which combined with quantum walk, which is an extension of Grover algorithm, can provide acceleration to TSP again, and also computing ground state of spin model and other kind of problems. Okay, so what's nice about this literature is there is no universal algorithm, right? For each problem that you care about, you require new ideas which are very specific to each problem. So that is something that requires a lot of algorithm design. So if you like algorithm design, this is a very beautiful area of research. Okay. So let's move to the next part, which is going to be something completely different. So it's no longer about Grover algorithm, it's about a different kind of technique based on the quantum Fourier transform. Okay, so we'll see how the QFT can help you speed up some optimization task. So yesterday we already saw application of the QFT, in particular in quantum phase estimation, which heavily use the QFT. But now we'll use the QFT in a different manner. We'll use it to compute the gradient of a function. Okay, so what is a gradient and why is it a useful object? So in optimization, like in continuous optimization, so you are optimizing over a continuous set of value, there is a very well-known method which is called gradient descent, and which is a very natural way of optimizing a function. The idea is to start at a point in the search space, and then you are going to do local move, trying to converge toward the minimum. And gradient descent tells you that you could just make a move in the direction which locally is decreasing the fastest. So you don't try to explore the entire search space at a time. You just look around you and you move in the best looking direction. So this kind of technique works very well in convex optimization, so when f is a convex function, and actually it will always converge to the global minimum of the function. When it comes to non-convex optimization, it can get stuck in a local minimum. Okay, so locally, this is a minimum, but there is somewhere else in the landscape something which is better than the current minimum. So in non-convex optimization, it is also used because finding local minima is often something that is useful to find global minima, and sometimes it's even okay to just converge to local minima. So that is a very important method. So mathematically, this is how you could phrase the gradient descent. So you take the derivative of the function, it's a vector of dimension d, and a gradient step consists of starting from the current iterate, making a move in the opposite direction of the gradient. So there are a lot of variants of this technique. Usually you will control the size of the steps, so there will be some prefactor delta which tells you how large the step is going to be. And then there are a lot of techniques to kind of accelerate the descent, and so on and so forth. So I'm just focusing on the most basic gradient descent method, but should keep in mind that there is a lot of improvement over this technique. So the question we are going to answer is how efficiently can we compute the gradient? Okay, this is a quantity that you need to know if you want to make a move. So how hard is it to compute the gradient? And in particular, what you should have in mind is the dimension of the problem, like how many inputs they are in the input space, is typically something which can be very large. Okay, so in many cases, the dimension is huge. So you would like the algorithm to have a complexity that scales not linear in D, but something even better would actually provide a significant speedup. So let's start with an easy case, okay, which is let's assume that locally, around the current point, the function is linear. Okay, so overall, it's not a linear function, but locally, if you just look around you, it behaves as a hyperplane. Now let's assume that you have an oracle for evaluating f. How many times should you evaluate f if you want to compute the gradient? So number of classical queries is going to be d plus 1. Essentially, what you want to do is you just want to have a system of equalities, of equations, of dimension sufficiently large, as large as the number of parameters in the linear function, which is d plus 1. So you just query d plus 1 independent points, and then you can just solve the system using Gaussian elimination, for instance, and then you will obtain the gradient of the function at the current point. Now, using a quantum oracles, we'll see in a minute that for such nice function, you can compute the gradient using only 2 queries. So this is called Jordan's algorithm. And maybe you already see how it's gonna work. So this is what we want to achieve. Well, this is extremely reminiscent of what we saw at the beginning of the lecture, right? It looks very similar to the Bernstein-Vazirani problem. Like the main difference is now we are working over the reals instead of working over Z2. Okay, and Bernstein-Vazirani, what we saw before is you can solve it using only 2 queries. So actually, this is the high-level idea of Jordan's algorithm. There is some painful calculation going on, so I'm not going to give you all the detail, but we are about to reproduce the steps of Bernstein-Vazirani algorithm. So if you remember, it was preparing a uniform superposition, making a quantum query, moving the function into the phase, undoing the query, applying a Hadamard. So it's about the same thing. So now we are over the reals, so we have to discretize the space in the right way. And the way it's done is by choosing a grid of points, so a discretized grid of points around the current iterate for which you want to compute the gradient, and prepare a superposition over this discretized grid of points using a finite encoding of the real numbers. And then you do essentially the same thing as Bernstein-Vazirani algorithm, so you make query in superposition, you move the result into the phase, and then you undo the quantum query. So doing that, you will arrive at this kind of state, which is a uniform superposition with information encoded into the phase about what is the value of f of x. And now the main novelty is to apply not the Hadamard, but the QFT, because now we are working over the reals, but it's pretty much the same. And the QFT will give you a state which highly concentrates on the binary encoding or the real encoding of the gradient. Okay, so I'm skipping a lot of details. The calculation is actually much more subtle than that, especially how to do the discretization. And the output is not exactly the gradient. It is the gradient up to some small error that depends on how good is going to be the discretization. So this is if the function is linear, I mean locally linear. So what if it's not linear? I mean in general the function is not linear. So well, you can just use some pretty straightforward ID, which is, as you know, there is like first order approximation, like Taylor approximation. So a function, if you look in a sufficiently small neighborhood, and if the function is not too bad, then you can approximate it by a linear function in which the linear term is actually the gradient. Okay, so what people have done is they studied under sufficient smoothness assumption, essentially f has to be analytic and the derivative has to be bounded in magnitude. So this contains a large family of functions known as Givry function. And in that case, you can estimate the gradient up to an error epsilon by doing, okay, not 2 quantum queries. In that case, you would need much more quantum queries, but still, it is sublinear in D. So it's about root D by epsilon. Okay, so the function doesn't have to be linear. It can be just satisfying this kind of condition. And then you have a quadratic speedup compared to the classical system solving algorithm. So that's nice. I mean, that is a provable acceleration. Now let me just mention, it's still a theoretical work. I mean, in practice, it may not be yet the most efficient application, but just to mention 2 caveats. One is you have to evaluate f with high precision, especially if it's far from being linear. And also, it may not be competitive against alternative classical method. And especially there are an important family of classical method, which is called automatic differentiation, which kind of opened up the box of the oracles. So right now we just assume that the only thing you can do if you want to have information about f is just making queries. Okay, you don't know how the oracle is actually implemented. Of course, in practice, there is some actual implementation, so you could just open up the circuit and look at it. And this is what is done, for instance, in automatic differentiation. And it may be more efficient than this kind of black box approaches. Okay, so it's a case-by-case analysis. But this is a potential quantum speedup when automatic differentiation is not possible to be applied. Okay, any question? Yes, please.
Do you need a quantum oracle for this real function f?
Yes, you need a quantum oracles.
How I mean, for the Boolean case, I understand that it's possible. Okay. For the real function, I can't see that you can have an oracle.
You mean?
Like implemented.
Okay, the question is, do you need a quantum oracle for f? And the answer is yes. Now, if the function is real, you would have to encode the outcome with a finite precision. So truncate the function up to certain threshold, which is also the case classically. I mean, no one is manipulating infinite numbers. So there is something going on in terms of how many bits of precision you need. And that, as I said, this may be an issue when applying this method because it may require applying the oracle with a very good precision.
So you evaluate the function classically to get outputs?
No, the idea is to really evaluate it quantumly. So typically, you would expect the function to be sufficiently simple such that you can construct a quantum circuit that evaluates it in superposition. Like you see, if the function is just an addition, let's say, you can efficiently compile a quantum circuit that would simulate the quantum oracle. The idea is that there are more complicated functions for which you would still be able to simulate the quantum oracle. Okay, but it may not always be the case. I mean, there is of course this question of how do you efficiently compile the quantum oracle. Any other question? Okay.
There is a question online.
Yes.
Which is why don't they use Jordan algorithms to compute the gradients instead of using classical algorithms?
So here what we propose is to use Jordan algorithm instead of classical method. So I don't really understand the question.
Okay, I don't understand that.
Okay. So yeah, just to summarize, I mean, what we saw is something which is an alternative to solving the system of equation, right? Instead of solving the system of equation, we'd use Jordan algorithm, which is quadratically more efficient than solving the system. Okay, so before moving to the next part, just want to say a few words about second order method. So gradient descent is called first order method because it only collects information and manipulates the first derivative, the gradient. Now you may want to use information about the second derivative of f, the Hessian matrix. And well, if you do that, so this is something which is also studied a lot in optimization theory. One advantage is it converges faster to the optimum in general. Now, the Hessian is harder to compute, and one important limitation is the Hessian is a matrix of size d by d. So now you want to manipulate something of like d square parameters. So storing the Hessian in memory can be much worse than applying first order method. So in terms of time complexity, it can be better, but in terms of space complexity, this kind of second order method can be limited by the size of the memory. And there have been a few papers recently that tried to accelerate second order method using quantum computing. So for instance, the interior point method has been looked at in these references. Okay. So let's move to the last part of the talk. And I want to show you a third family of optimization technique using quantum oracles. So this last family is based on Monte Carlo sampling. So Monte Carlo algorithm, it's an important family. It's a paradigm of algorithm design in which we try to use random sampling and statistical estimation in order to accelerate the execution of an algorithm or improve the performances of the algorithm. So that's a very important family of techniques. For instance, stochastic optimization is based on this kind of techniques. Now, quantum computing is a very good candidate at accelerating Monte Carlo method because, as you may know, there exists certain probabilistic distribution for which we expect quantum computers to be much more efficient at sampling from those distributions. I mean, if you heard about the Google quantum supremacy experiment, that Google claimed to have identified a particular distribution which they were able to sample from using their machine and which is believed to not be efficiently samplable using classical machine. Okay, so sampling is really something which is expected to be a good candidate for quantum speedups. Now, unlike Google, what we want to do is identify distributions which are relevant to some problems of interest in optimization. So we'll see two techniques in which, using the ability of quantum computer to sample, we can accelerate some optimization tasks. The first one is about linear programming. So this is the following problem, which I think you all know about. So we want to minimize a linear function. So here there are two variables subject to a bunch of linear constraints. Okay, so typically we have a graphical representation as a hyperplane. So here the region in blue correspond to all the points satisfying all the constraints. And among those points, we want to find the one that minimizes the objective function. So this is the convex optimization problem. So if you remember, convex optimization implies that you can efficiently find the minimum. Here the question is going to be, how efficient can you be in finding the minimum? Like you really want to optimize the complexity as much as possible. The setup is that the coefficient of the LP are going to be provided by an oracle. Okay, so you can query the LP in superposition. And you want to find an approximate solution up to distance epsilon. Okay, not the exact one, but approximate it with some precision epsilon. And this is what we're going to see. I will show you a quantum solver that requires a sublinear number of quantum queries to the oracle, like sublinear in the number of variables and the number of constraints. Now, classically, the literature is a bit complicated to explore, but essentially, you always need at least n plus m classical queries. Classically, you can improve the dependence on epsilon a lot, but you always have to pay at least that many classical queries. So the speed up is with respect to the dimension of the problem. So, okay, let's try to give you some ideas about how it works using Monte Carlo sampling. So again, we are going to start with a classical algorithm, an old one, a very famous one, which is called the Grigoriadis-Kashian's algorithm, which is based on a technique called the multiplicative weight update method. It's not gradient descent, but there exists some connection which I will not talk about. So first step is to reduce a linear program into a nice problem, which will be nicer to solve. So I'm not going to give you the reduction, how it is done. I'm just giving you the final object. So essentially, instead of solving an arbitrary linear program, you can focus on the following problem. So now you have a matrix A. Essentially, this is a matrix encoding of the linear constraint. Okay, we just put the linear constraint into a matrix that contains the coefficient, and we apply a few more transformations. So A is skew symmetric, meaning that A transpose is equal to minus A, and entries has been normalized to be between -1 and 1. Not very important for us. Second point is very important for us. Instead of exploring the entire search space, we can only explore solutions which correspond to probability distribution. Okay, so X, this is what we are looking for. And we know that it is a non-negative vector in which the sum of the entries is equal to 1. And the goal is not to optimize something, it's something else. The goal is to find X in this search space that satisfies the following condition. So the matrix vector product between A and X, each coordinate has to be less than epsilon. Okay, so it turned out that there always exists such a solution. This is related to Nash equilibrium, and actually there even exists a solution that makes the matrix vector product equal to the all zero vector. Okay, so in some sense, we know the optimum exists. We want to approximate it up to a threshold epsilon for each coordinate. And again, if you know how to solve this problem, you can solve linear programming as well. Okay, so let's focus on this problem and how to solve it. So of course, what's going to be used is the fact that we are looking for a probability vector. We know the solution is a distribution, so we'll try to explore the set of probability distribution. And we'll use the following on that. So we'll focus on so-called Gibbs distribution, in which x is of the following type. It is proportional to the exponential of epsilon a times u, where u is an integer valued vector. Okay, so what do I mean by the notation on the top? So xi, so each coordinate of x is equal to e epsilon a I u divided by z, okay, where ai is the highest row of A, and Z is just the normalization factor. We want it to be normalized, so it's just going to be the sum over all I of E epsilon A I U. So this is what I mean by the Gibbs distribution. It's a very important distribution, studied a lot in physics. Okay, so we'll be looking for a distribution of this type, and the question is, how should the vector U, how should it be chosen? So this is the algorithm. Again, it's going to be an iterative process. So we'll start with something easy, which will be gradually updated. So initial step is to choose U to be the all zero vector, meaning that the Gibbs distribution is a uniform distribution. This is our initial guess. Now we repeat the following process. We sample one index, so one row of the matrix A, by using the current Gibbs distribution. Okay, so you set up the distribution, sample a vertex, you obtain a random outcome, and what you do is you update the vector U by doing +1 on the highest coordinate. So you update, you increment one coordinate of U, and you increment the time step. Okay, so it's extremely simple. Why does it work? Well, again, I'm not going to do the analysis, but intuitively you can convince yourself that if there is a violated constraint, so if there is an I which is more than epsilon, or the largest the product is, the more the distribution will give you these indices. So the distribution is pointing toward the indices that violate the most the inequalities that you want to satisfy. So it's kind of a random way of updating your distribution by correcting the distribution in the most violated direction. Okay, so there is a beautiful mathematical analysis that shows you that if you just repeat this process log n by epsilon squared times, it will converge to an epsilon solution to the initial problem. Okay, and each iteration has cost capital N. So classically, the complexity of this kind of linear system solving is going to be n plus m divided by epsilon squared, up to some log factors. Now, quantum speedup. The quantum speedup, so the overall structure of the algorithm is going to be preserved. The quantum speedup is occurring in this step, the one where we are sampling from the Gibbs distribution. And the idea is pretty straightforward. If we were able to prepare the corresponding quantum state that encodes the distribution into the amplitude, then we could just measure the quantum state, collapse it to an index, and then use this index to update the ansatz. Now, the point is, you can show that preparing this kind of quantum state can be done using root n queries instead of n classical queries. So there is some dependence on epsilon that I am omitting, but with respect to the dimension, you have a quantum speedup. Okay, so just to give you a very high-level idea about how quantum state preparation is performed for this kind of ansatz. So you start with a uniform superposition. This is very easy to prepare. Now, this is the step which is hard to do or to explain. So using what you saw yesterday, like technique like block encoding and quantum singular value transformation, so these are kind of advanced quantum algorithm for manipulating matrices, you can map the uniform superposition to something that contains the encoding of the Gibbs distribution into the phase up to some garbage state. Okay, so this is something non-trivial to do, again, based on some advanced algorithmic technique. And finally, you can just amplify the good part of the state, the part in which you have correctly computed the Gibbs distribution. You kind of renormalize this part to get rid of the bad part of the state, and you will arrive at the correct final superposition, which you can measure in order to execute your algorithm. Okay, so that is the high-level idea of the quantum linear system solver. Is there any question? So this is the references. If you want to know more about how it works, there is some nice data structure which are also used to prepare the quantum Gibbs state more efficiently. So there is very beautiful algorithm ID which are going behind this kind of techniques. And actually, you can even push this technique even further. You can solve the so-called semi-definite program, which is an even larger class of optimization than just linear program. Now you are optimizing a linear constraint, but the variables x is a matrix, and it has to be positive semi-definite. It's a very important class of optimization, which is also harder to optimize, but using quantum Gibbs sampling, you can now prepare ansatz which correspond to density matrices proportional to some exponential of quantum Hamiltonian, of Hamiltonian. And then again, you can apply similar IDs, much more advanced, which also give you some speed up in some cases. Just to give you two limitations of this family of techniques. One is, or three limitations. One is the scaling with the precision is not that good compared to classical techniques. It requires involved quantum circuits for performing arithmetic operation, quantum singular transformation, so on and so forth. And also, for concrete LP and SDP of interest, it may perform worse than alternative classical method. So it's theoretical result, but we are still far from application on concrete problems. Okay, so to conclude, a very last application, which I like a lot, which is going to be about escaping saddle points. So we are back to the gradient descent or gradient techniques. And in gradient descent, there is something called critical points, which are points of the space in which the gradient is equal to 0. So if you are doing gradient descent, if you remember the gradient update, you are moving in the opposite direction of the gradient. So if it is equal to 0, then you are not moving anymore. So there's three cases in this case. If the function is non-convex, either it is a local minima, a local maxima, or a saddle point. So the last case would not occur in convex optimization. This is only for non-convex optimization. So a saddle point is not an optimum, not even a local optimum. It's just something else in which the gradient is equal to 0. Okay, so I'm plotting two examples of saddle points on the right. One is for the cubic function. At the origin, there is a saddle point. So the gradient is equal to 0 in all directions. So what should you do? I mean, you are stuck at a point where the gradient tells you nothing about how to move into the optimization landscape. So two techniques which can be used is, one is to look at the second order derivative, the Hessian, but as we said before, that may be too expensive to do. Another technique is to use Monte Carlo sampling and to kind of perturbate the current iterate with some probability distribution. So you have a choice, you have a chance of making a move in a direction that is kind of helping you escape the saddle point. Now, of course, the crucial question is, how should you choose the noise? Like, what kind of distribution will give you the higher chance of moving toward the the local minimum or the minimum value? So there was a suggestion in this paper on the right of choosing the noise by solving the Schrödinger equation and sampling from the resulting state. So it does the following thing. We consider the Schrödinger equation with, it's a real dynamics, so x is a real numbers. It is going to be the point in which you want to move in order to escape the saddle point. And it's evolving over time according to the kinetic operator and the potential, which is your function that you want to optimize. Okay? So this is just an instantiation of Schrödinger equation using the objective function f. Now, the initial condition at time t equals 0 is to have an isotropic Gaussian distribution, which is centered at the saddle point. Okay, so initially your distribution is just like uniformly Gaussian around the saddle point. So you have the same chance of moving into all directions. Now, what will happen if you make the state evolve according to the Schrödinger equation? So the idea is to prepare psi-t using quantum Hamiltonian simulation, which can be done efficiently on a quantum computer. This is where the quantum advantage is coming from. And then you will measure the state, and it will tell you what points you should use to escape the saddle point. So it turned out that the final result, which I'm not going to detail, is if you do that, there is an improved scaling in terms of cost with respect to the dimension compared to classical method. And just to give you an idea of why it works. So the idea is, again, to look at Taylor approximation. And now we'll look at second order approximation centered around the saddle point. So there is a first order term which corresponds to the gradient. And this term is equal to 0 because by definition we are stuck at the saddle point. And now the second order term contains information about the Hessian. Now what can be shown is that psi tx, if you make it evolve according to a quadratic function, as is the case when you use the Hessian, then after a time t, it will still follow a Gaussian distribution, like multivariate Gaussian over d dimension. However, it's not going to be isotropic anymore. So there will be some direction of the Gaussian which are more likely than other direction. And if you do the math, you can actually show that the most likely direction are going to be the one that points toward the area of the landscape where the curvature is negative. Okay, so there is some mathematical statement showing you that the covariance matrix of the Gaussian is pointing you towards the direction in which you really want to move if you want to make your objective function decrease. Okay, so that's all I want to say about this algorithm for saddle points. And with that, I think I will stop here. Thank you.
Okay, is there some questions? So there is a follow-up about the question about the Jordan algorithm that was online. It's like in a lot of application, people are using, like in quantum machine learning, for instance, to compute the gradient, they are using classical optimizers instead of the Jordan algorithm. Is there a reason why, or?
Well, I think it's because Jordan's algorithm is still too expensive for current architectures. So there is a QFT hidden inside. So that is something which is very expensive to use in practice.
So you mean more than a classical optimizer?
I think so. So I don't know exactly how they compute the gradient in that case, but I think so. I think it's more expensive.
Okay, thank you.
Well, you could just do classical finite difference method, which would be much cheaper in terms of quantum resources than using the QFT.
Other questions? Okay, so I have two questions. So first, for the gradient, okay, can you build better oracle for if it is very sparse? To have like Nesterov algorithm to make some acceleration of gradient?
Yeah, that's a good question. I don't know. So, like sparsity is a natural assumption. I think that has not been studied really. So, yeah, I don't know.
And the second is perhaps more hypothetical. For the Asian case, okay, do you think that you can build an oracle to make just like a BFGS algorithm to have a numerical approximation of the Asian without making derivation?
So the Asian, you can also estimate it using similar technique as Jordan's algorithm, actually.
Yeah.
You can also recover the parameters and achieve a quantum speedup. So the scaling would still be higher than what is needed for the gradient, but that would give you an improvement. So I don't know if in this kind of application it would be better than currently existing methods.
At least the convergence rate is quadratic.
Yeah, it's quadratic,
linear,
yeah.
So.
But I think the memory is often an issue when you manipulate the Asian. And actually there are some theoretical results that tells you that the faster convergence rate provided by second order method cannot be achieved if you don't use a large memory. So there is no memory efficient methods for some families of functions. So there is really a trade-off between memory and convergence rate, which cannot be avoided classically. But that would be interesting quantumly if it is possible to have both a fast convergence and a memory efficient algorithm. And I think it's completely open to answer that question.
Thank you. So is there some other questions? Yes.
Hi, thank you for the lecture. It was really nice. I would like to ask, from the algorithms presented today, does any of these algorithms can be implemented in noisy hardware towards large-scale applications, for example, with 15 or 20 qubits?
So you are asking if you can implement them on like a few qubits? That is the question?
In real quantum hardware with 15 to 20 qubits.
Well, I don't know. So whenever you can apply the QFT or Grover algorithm, this kind of algorithm, then you would also be able to apply this kind of technique. I'm not sure the QFT or Grover can be implemented, I mean, even, except on a very small example, but I don't think they can be implemented on small architectures. They require quite a lot of resources compared to what we have right now. So these are really the long-term perspective, I would say.
Other questions? Okay, thank you, Yassine.